Hello. We will integrate the metabolism today within the different cells that we learned about, and also we will talk about the feed-starve cycle, which is integration of metabolism among. So I will go through the major metabolic pathways in some of the cells, including the brain, neuronal cells, red blood cells, skeletal and heart muscle, adipose tissue, and liver. Then we will switch to the caloric homeostasis, which means that we need to have energy supplying molecules carried in our blood for all of our cells every moment of our life. We will review the regulation of metabolism by hormones. We will talk about the glucoregulatory system, and as a demonstration of how the hormones work, where the fuel molecules come from, and how these pathways are up or down regulated to serve us, I will go through the feed-starve cycle. And as a summary, we will look into glucose and caloric homeostasis, the function of the liver, and how these calories, how these molecules are used. Again, the Word file of this particular lecture will be posted in the Basic Metabolic Pathways folders. I found a couple of videos that if you have time, you may be able to watch. Um, and the resource material again is suggested to be looked up in Lippincott. So you learned about most of these metabolic pathways. We went through the glucose and carbohydrate metabolism in great details. We also talked about amino acids and how they can be utilized to produce energy and glucose and potentially lipids. The only thing that we have not talked about it yet is the fatty acid and triglyceride metabolism and the ketone bodies, but it's coming soon. So the organ-specific pathways that I wanted to go through at first, just to remind you what the different molecules, depending on their nature, can do, what fuel molecules they can use, what the energy generating pathways are, whether there are energy storage capacity in every cell, and what other special pathways can be run in our cells. Then we go to the homeostasis that we need to maintain in our body, including caloric and glucose metabolism dictated by hormones. This section is out of a very simple book, which is PDQ Biochemistry, pretty darn quick bio. Uh, if you have time, just read it. It is kind of funny and it brings home the message of the nature of the different cells related to their metabolism and use of energy carrying molecules. So the brain is the spoiled child, always needs glucose, whatever happens. Liver is the provider and orchestra leader. You already learned about it a lot. Muscle is the bodybuilding sibling, which takes a lot of energy for its work. And adipose tissue is the couch potato, which majorly just stores away fatty acids, of course, for good reason. So let's start with red blood cell. And you may remember that it is a very poor cell in regard of what it can do. No mitochondria, so very anaerobic. The only fuel source is glucose. Glucose is going down in glycolysis, but it ends up in lactate because there is no mitochondria. So red blood cell is a constant glucose user and a constant lactate producer. You may recall that we talked about red blood cells, kind of a shunt in glycolysis that will produce 2,3-BPG, which is absolutely important for downloading oxygen from hemoglobin, which have thousands of copies in a single red blood cell. We also talked about the importance of the pentose phosphate pathway in regard of keeping the glutathione system healthy, which is used in red blood cell to fight the oxygen radicals, because oxygen is carried, oxygen is always there in these cells, and radicals are produced which would damage the membrane if the glutathione system would not be there. We also mentioned, if you recall, that there is a huge difference between mature red blood cells and reticulocytes. Reticulocytes have mitochondria, which means that they can use additional energy-carrying sources like fatty acids, and they can also use glucose to actually burn it to carbon dioxide and water, which produces much more energy for the reticulocytes. They have in the immature form, in reticulocyte form, they have all the other organelles, including nucleus, to drive cell division. All right, so let's see this spoiled child, the brain. The brain is a aerobic tissue, very high respiratory metabolism. Consequently, it uses a lot of oxygen. If oxygen source is not enough, you will feel it right away because you will feel dizzy and probably pass out. There is no significant fuel reserve. We talked about it that every cell can store away a tiny little bit of glycogen, but it is not significant, not substantial in case of the neuronal cells. So continuous supply of energy is needed, and the preferred supply is glucose. There is a GLUT3 transporter on the neuronal cells and a GLUT1 transporter on the blood-brain barrier. None of them are regulated. What dictates these transporters to work is the concentration difference between the outside and the inside of the cell. Now you know that the only glucose being the preferred resource has a good reason that even if they are aerobic cells and have mitochondria, they cannot use fatty acids because the blood-brain barrier doesn't let through long-chain fatty acids. What else can they use? When we starve and the liver is producing ketone bodies, then ketone bodies actually can get through the blood-brain barrier, and they are short lipid-based energy-carrying molecules supplying acetyl coenzyme A, which can go then to Krebs cycle and terminal oxidation to produce energy. However, ketone body utilization always be shared with glucose utilization, whatever happens, whatever starvation we go through, some glucose will be always taken up by the neuronal cells. So the glucose is the major energy-carrying molecule. Lots of ATP is produced by glucose, more than from anaerobic, definitely. And the pentose phosphate pathway is also will use glucose. Pentose phosphate pathway and the production of NADPH is mainly important for biosynthetic purposes for the neuronal cells. You may recall that there are a lot of fatty acids and long chain fatty acids produced and used in the shield, the outer shield of the neuronal cells. Energy is used for survival, for production of neurotransmitters, for the function majorly of the neuronal cells, and you will learn more about it in 2 blocks away in the neuroscience block. Skeletal and cardiac muscle, they are also very aerobic, except for the white muscle cells. The red muscle cells and the cardiac muscle cells have a lot of mitochondria, and they use a lot of oxygen. So let's focus on the skeletal muscle first. It can work under anaerobic conditions, producing lactate when oxygen supply is not perfect, but mainly they use oxygen and they work under aerobic conditions. Glucose is one of the major supplies of energy, of course, and skeletal muscle cells can store away glycogen for later use. Glucose usually goes through the aerobic pathway, going to the mitochondria, pyruvate going to the mitochondria, and etc. And when oxygenation is not enough, then lactate is produced. You remember that GLUT4 is the typical glucose transporter. When there is enough glucose available, or excess glucose available, it is insulin stimulated. So it means that the skeletal muscle can take up more glucose and help to reduce the high circulating glucose level to normal level after we have eaten. Now, what else can be used? Proteins can be degraded in the muscle and can be shuttled in the form of alanine to the liver for gluconeogenesis, but also amino acids are taken up in a well-fed stage and used for either energy or mainly rebuilding the muscle proteins. Now, when glucose supply is decreasing, GLUT4 is not in the cell membrane anymore. Adipose tissue released fatty acids can be taken up for energy, since this is an aerobic cell. And ketone bodies, also produced during starvation by the liver, can come in and also be channeled to the Krebs cycle and terminal oxidation. So at rest, what can be used? Stored glycogen, fatty acids, glucose, ketone bodies, and phosphocreatine. Now you remember that phosphocreatine and glycogen majorly stored away to aid muscle work. So phosphocreatine at exertion can supply energy for as long as a couple of seconds. Glycogen mainly at energy burst for a couple of minutes, and glucose and fatty acids can be used for longer time periods. Glycolysis can produce lactate, which can go for the Krebs cycle back to the liver. And as I mentioned, fatty acids are happily used because fatty acids produce more ATPs than glucose molecules. Excessive activity and fasting, as I mentioned, protein degradation is initiated and amino acids are going to the liver through the alanine cycle to produce substrates for gluconeogenesis. Now, just a little comparison between skeletal muscle and cardiac muscle. For cardiac muscle, there is no rest period. Cardiac muscle always needs to work, and it is very highly aerobic. Even more mitochondria than in the skeletal muscle can be found in cardiac muscle. So full oxidation of glucose and happily used fatty acids. So under normal conditions, glucose and fatty acids are used. Lots of ATP is produced for function. During starvation, glucose is not taken up anymore, but fatty acids that are coming from adipose tissue and ketone bodies that are coming from the liver are used for energy. So let's see this couch potato, adipose tissue, which mainly is really the storage facility for triglycerides. So 65% of its weight may be full with fatty acids. It is usually in a well-fed individual, usually is enough for 3 months supply of energy. But the average turnover is approximately 2 days, which means that fatty acids are taken up and stored away and utilized, released when there is a need for fatty acids by other tissues to be utilized for energy. You may recall that adipose tissue also has GLUT4 in the cell membrane by insulin stimuli. So adipose tissue is also responsible to taking up more glucose, turning it into glycogen and fat, and in the meantime reducing circulating glucose level to normal after we have eaten. Glycolysis runs for energy production, and when a lot of glucose is coming in, can be used for fatty acid triglyceride synthesis and storage. Pentose phosphate runs to aid this synthetic process, and ADPH is needed for biosynthetic processes. When we starve, this fatty acid storage, actually triglyceride storage, will be mobilized, and fatty acids and glycerol will be shuttled out to the circulation. Fatty acids are used for energy. Glycerol can go to the liver to aid gluconeogenesis. You may recall that for gluconeogenesis, liver needs energy, which comes from beta oxidation of fatty acids, and glycerol is actually a 3-carbon substrate to produce glucose. Fat, when it comes into for storage, it comes from 2 sources. One is from a dietary source, bringing here by chylomicron particles, and the other is liver newly synthesized fat, which is delivered by VLDL. So here is liver, and it is really something that you already learned. It is just an overview to remind you how important metabolically liver is for us. So this is a general hepatocyte, which is doing a lot of metabolic processes for us. And also, please don't forget that liver is also the detoxification center of the body. Lots of proteins that are synthesized for the serum, with a lot of function in the serum there. Now, start the metabolic process. So we have glucose coming in. And you recall that the typical glucose transporter on the hepatocytes is GLUT2. GLUT2 is taking glucose from the environment, but GLUT2 is also used to push out glucose when there is a need to balance the blood glucose level. So GLUT2 is aiding glucose to come into the cells when there is plenty circulating in the blood. Glucose and actually amino acids are entering the liver right away after we have eaten, you remember, through the portal vein. So what happens to this glucose? This glucose is going in, and it is used for glycolysis. It is used for glycogen synthesis. It is used for pentose phosphate pathway to produce NADPH for biosynthetic purposes, and also because the detoxification process is running independent of whether we eat or not. Glucuronides, there is a typo here, glucuronides are synthesized, glucuronic acid is synthesized that aids the elimination of certain metabolic byproducts and toxins, including bilirubin. So what happens to the glucose is going in glycolysis, and because we have extra glucose, it will be used for fatty acid and triglyceride synthesis, packaged in VLDL and released to the circulation. Please remember that cholesterol is also produced and packaged in VLDL. So glycolysis is running for energy production. Glycolysis is running to store away energy in the form of glycogen and to store away energy in the form of fat, majorly triglycerides. So what happens when suddenly glucose source diminished and liver is here without glucose? So what is the function of liver in this case is actually to produce glucose. So when glucose is produced, it can come from 2 sources: glycogen pushed out through GLUT2 as in the form of glucose, and also gluconeogenesis. Now, gluconeogenesis will start either from amino acids that are coming from the muscle, and push through the gluconeogenic process, and glucose is secreted by the liver. Or, and this is why I put a huge exclamation mark here for you, comes from lactate. Liver is not really a lactate producer. If it produces lactate, we are in trouble. But it can take up lactate, and that can shovel lactate depending on what phase the liver is. If it is under insulin signal, it will produce energy from lactate. If it is under glucagon signal when we fast, lactate will be shuttled into gluconeogenesis and produce glucose. So please remember that this is one of our tissues that is hormone sensitive, and depending whether insulin or glucagon is signaling to the liver, different pathways will be up or down regulated. So during insulin signal in the well-fed state, glycolysis, fat synthesis, cholesterol synthesis will be running, and NADPH is hexose monophosphate shunt. NADPH is necessary for fat synthesis. During fasting, muscle release amino acid, adipose tissue will release fatty acids. Both of them are coming to the liver. Fatty acids aid for energy production, and amino acid aid for gluconeogenesis. Please remember, again, it's just a reminder, urea cycle must run when amino acids are entering and used for gluconeogenesis, because we need to eliminate the amino group and ammonia. And when we starve and fatty acids are coming into the liver, they will be used for energy, but they also will be used for ketone body synthesis to aid the other organs that can use this small lipid-based energy, including the central nervous system and skeletal and heart muscle. So let's switch to regulation of these metabolic pathways. Regulation is done through substrate availability, of course, but mainly regulating the key enzymes in the metabolic processes. Some will be regulated by negative and positive allosteric effectors, and some will be regulated by covalent modification of the key enzymes or induction and repression of the synthesis of the key enzymes. Please remember these 3 and 4 are manifestation of the action of the hormones of key cells. Let us go through very quickly. Again, this is a reminder that you learned a lot in physiology, that there are majorly 3 main hormones, and that glucocorticoids also help when we starve, which will act on 3 different cell types: liver, muscle, and adipose. The other cells are not hormone sensitives, so even if we have insulin or we have glucagon, epinephrine, or glucocorticoid levels going up in the circulation, only these 3 cell types will be sensitive to hormones. So insulin is sensitive to, insulin is sending the signal to liver, muscle, and adipose tissue or cells. Glucagon is liver and adipose. Muscle is not sensitive to glucagon. Epinephrine, however, will send signal, this is the stress signal, to liver, muscle, and adipose. Glucocorticoids also act on all 3 cell types, but mainly will act on liver in aiding glucose production. Very funny to see, actually. Funny or not funny, this is reality. Insulin is the only hormone that stimulates the storage of fuel and other bioactive, biosynthetic pathways. All the other 3 hormones are counter-regulatory to insulin. All right, so again, review. Glucagon is acting through glucagon receptor, and this is a G protein coupled receptor, activates adenylate cyclase, cyclic AMP is produced, which will activate cyclic AMP-dependent protein kinase. This kinase will phosphorylate key intermediates in the signaling pathway or directly phosphorylate key enzymes in metabolism. So what is the effect? Upregulating glycogenolysis, gluconeogenesis, lipolysis, ketogenesis, and uptake of amino acids. Glycogenesis will be downregulated. All right, let's see insulin. Insulin is a receptor tyrosine kinase. Two of the receptors need to come together to accept insulin and upregulate the downstream signaling pathways. Many pathways are upregulated by insulin. What we are focusing on are twofold. One is, which is not labeled here, is actually is labeled but not separately, glucose uptake. So this is one of the signaling pathway which will place GLUT4 transporters from cytosolic storage to muscle and adipose tissue cell surfaces, so aid these two tissues to take up more glucose. Other pathway that will be upregulated, and please remember this is actually the phosphatases that are upregulated at the end of the signaling pathway. So these enzyme glycogen synthetic enzymes will be upregulated, protein synthesis will be upregulated, fat synthesis will be upregulated, while the other processes will be downregulated. So you already see that glucagon and insulin are upregulating opposite pathways from each other. When we talk about epinephrine, epinephrine can go through the same pathway. Adrenergic receptors can be either acting through G proteins or other receptors too. And glucocorticoids being corticosteroids, they will not have a cell surface receptors, but they go into the cytosol and into the nucleus, and they will aid in up or down regulation of the synthetic process, transcription, translation of the enzymes that they regulate. So what are the signals for hormone release? Again, physiology will talk about it in details. So I will be really short. The glucoregulatory system, insulin or glucagon production, different substrate will signal to the pancreas, alpha or beta cells in an opposite way. So let's start with insulin. When we have eaten and the circulating amino acid and glucose level will be high in the circulation, they are majorly the positive signals for insulin release. Epinephrine, a stress response hormone, is actually stopping insulin release from the beta cells. So what happens when the glucose level is dropping in the circulation? So when we have high glucose, it halts glucagon release when it helps actually glucose, when it helps insulin release. But when epinephrine, a stress hormone, will be released and amino acids start to be released from the skeletal muscle, they will send a signal to alpha cells to release glucagon. Okay, so this negative glucose inhibition is released, and positive epinephrine and amino acid aid the release of glucagon. Now, I put it here for you, just the glucoregulatory system, little figure that I really like, that what happens in the circulating blood, that glucose level is going high after we have eaten, and then because every cell starts to take glucose away in the postprandial period, and also because GLUT4 is up in muscle and adipose tissues and take more glucose away, it starts to be reduced, the circulating glucose level. When circulating glucose level is going down and it hits about 70 milligram per deciliter, epinephrine and glucagon start to be released to counteract this dropping glucose with stimulating majorly the liver to produce glucose. Later on, if the glucose level is still dropping, growth hormone and cortisol will help in aiding in stimulating liver to produce glucose and put back the glucose level into normal. Now, what if these hormone signals are not enough and the blood glucose level is dropping further? At around 60, you will feel some signals, which we call adrenergic symptoms, anxiety, palpitation, tremor, and sweating, which is a sign of low circulating blood glucose, while then it is dropping further, the uroglycopenia symptoms will be up, headache, confusion, slurred speech, seizures, coma, and even death can occur when circulating glucose level is dropping further. Now, this is a little figure that you may want to remember later. So the low blood glucose will send a signal through the hypothalamic pituitary regulatory system through the autonomic nervous system that will release norepinephrine, or through the pituitary ACTH adrenal system, which will produce epinephrine and also will release cortisol for us. Autonomous nervous system also signals to the pancreas, so already low blood glucose level, epinephrine signals to the pancreas to release glucagon. So glucagon is aiding the glycogenolytic system and also the gluconeogenic system to upregulate glucose release from the pancreas. Epinephrine will majorly upregulate glycogenolysis, and cortisol mainly upregulate gluconeogenesis. So many systems will upregulate the production of glucose by the liver. Well, because dropping blood glucose can result in death, so we need to assure that we have enough glucose in the circulation. So, when blood glucose is dropping, we call it hypoglycemia. Please remember, hypoglycemia is never normal. What are certain causes that can result in hypoglycemia? One, insulin induced. So it occurs in diabetic patients if they don't titrate well insulin to what they have eaten. And if they inject more insulin than necessary, then insulin will aid in clearing that glucose from the circulation. So diabetic patients in this case can go to hypoglycemia. Another reason is so-called postprandial hypoglycemia, which is transient, and hypoglycemia will be induced by exaggerated insulin release by the pancreas. It is one of the signs that there is a problem with insulin regulation, so it can be a sign of early sign of insulin diabetes. What these people need to consume is frequent, smaller meals rather than one large meal that will spike the insulin very high. So what is fasting hypoglycemia? Again, it is not normal. When you fast, you still have your liver to produce glucose, so you should not go to hypoglycemia and hypoglycemic shock. So it is a sign of a problem of gluconeogenesis by the liver. It can happen, you already learned about it, in hepatocellular damage. It also can happen in adrenal insufficiency when not enough epinephrine is produced or glucocorticoids. It can be a sign of overproduction of insulin by the pancreas, and it could happen in pancreatic beta cell tumors. I just wanted to remind you that you learned one of the glycogen storage diseases, glucose 6-phosphatase deficiency, that will lead to hypoglycemia because this is the last enzyme of the glycogenolytic and gluconeogenic process. So in glucose 6-phosphate deficiency, you remember it is von Gerke's disease, glucose will not be released by the liver, or lesser glucose will be released. Now, alcohol-induced hypoglycemia. You also learned about the effect of alcohol, that alcohol dehydrogenase in the cytosol will produce NADH, which will actually inhibit gluconeogenesis because it will push the gluconeogenic substrates back to their reused form. So gluconeogenesis cannot happen. So when you consume ethanol, you need to think about it. It is especially serious when you already depleted your glycogen stores with exercise or with fasting, and now you drink alcohol in a larger amount, which will stop gluconeogenesis, so your body will not have the resources for glucose because the liver will not produce glucose. Now, this is the summary of this first section that I talked about, the effect of insulin, glucagon, the different pathways, and the different examples of hypoglycemia. Let us switch to the second part, where I will demonstrate through the star-feed cycle how the glucoregulatory process is working and how the metabolic pathways for fuel storage or fuel demand, how these organs will work together to supply enough energy-carrying molecules in the blood so that every cell of ours will get energy. So let's see, the first step is the so-called first stage is the so-called well-fed or absorptive stage. Depending on how much you eat, depending what you eat, it could take 2 to 4 hours after meal to absorb the energy-carrying molecules distributed among the cells and making every cell happy. So what happens when we have eaten, this is after meal, well-fed state, absorptive state, that insulin level will be high and the counter-regulatory hormone levels will be low. So insulin will dictate what happens in those 3 tissues that are insulin sensitive. You remember, liver, adipose, and muscle. The other cells are just happily taking glucose or whatever is coming in their ways. The metabolic processes will be upregulated depending what is getting into the tissues. So, glycogen synthesis to store away energy-carrying molecules will be especially important in liver and muscle, although every other cells can store away some glycogen. Glycolysis will run, especially in the liver and adipose tissue, to store away fat, to produce triglycerides, and store it away. Pentose phosphate pathway is running to aid the fatty acid synthetic process. Lipogenesis, triglyceride synthesis in adipose, in liver, producing VLDL, putting it out, adipose tissue taking it up, storing it away. Cholesterol synthesis in the liver, taking advantage of the incoming glucose, cholesterol is synthesized, packaged also in VLDL, and released to the general circulation for other cells to take cholesterol. Protein synthesis in every tissue. This is the time when you can replace your proteins, when you can produce serum proteins by the liver and other structural and functional proteins in the cells. However, protein degradation, lipolysis, fatty acid beta oxidation, glycogenolysis, and gluconeogenesis will be downregulated. So here is the picture that will show you what is happening, and I always list here what are the pathways that are upregulated by those tissues that are hormone sensitive. So again, this is insulin, portal vein is getting glucose and amino acids, fats are packaged in chylomicrons and go through the lymphatic, go to the general circulation. So glucose and amino acids go through the liver makes a decision what to do with them. Glucose will be used for glycogen synthesis, for fat synthesis. VLDL is produced and produces and delivers the lipids, every kind, including cholesterol, to the target tissues. So amino acids are also distributed, and although not every tissue and every cell is labeled here, they will get amino acids to produce their proteins. What is getting back to the liver is lactate from the lactate producing cells. I'm not really happy that muscle is labeled here, although remember, white muscle cells are lactate producers. All right, so you have eaten, 2 to 4 hours passed, everything is taken up from the blood glucose went back to normal. Now we are entering the so-called between meal or very early fasting stage. Depending on what you are doing, please don't memorize these hours, but it is approximately between 4 and 12 hours when this particular state of hormonal and metabolic state will last. If you eat a very small meal, which already everything was utilized within an hour or two, then this early fasting state will start earlier. If you had a huge meal and then you went to sleep, this early fasting state will last longer. Majorly, what is the typical scenario here? Insulin now is not released. Glucagon and epinephrine will be released from the pancreas or the adrenal medulla. So these are the hormones that will upregulate the utilization of glycogen and the release of glucose from the liver. It will also signal the liver to start gluconeogenesis from majorly lactate from the lactate producing tissues, and some amino acids may also be released from the muscle to feed to gluconeogenesis. Lipogenesis, protein synthesis, in the meantime, will be downregulated. So mainly it is the liver, and mainly at first is glycogen, which is supporting the balancing out the blood glucose. So this is a figure to demonstrate it. You see the liver is active, majorly using glycogen. Glucose is going to every tissue to feed them. And what is coming up is mainly lactate from lactate producing tissues, and some alanine start to go to liver for gluconeogenesis. So if we don't eat for longer than this between meal period, we enter the fasting and later the starvation period. Typical in this period, either early or late, that insulin will be low, glucagon, epinephrine high. Later on, glucocorticoids are released, and also thyroid hormones will be released to reduce the basal energy requirement of the tissues. When the thyroid hormone level will be low, then the whole metabolism is slowing down, and the whole and you will feel sleepy and tired. Majorly, it is the sign to slow down because not enough energy carrying molecules are available. So early fasting state, again, the numbers are approximate depending on what you are doing. It can be from half a day to 2 days. Again, depends on what you have eaten, what you stored away, and how long you have, and what you did. You did run the marathon, or you went to sleep, or in between. It could be 0.5 to 2 days. So You remember, insulin is low, all the other hormones are up, majorly in early fasting state. Glucocorticoids are not playing a big role, but glucagon and epinephrine does. So glycogenolysis is going on further, but the glycogen store that the liver can store away is majorly used up within potentially a day or so. So this is why I put here, anti-stores are diminished. Gluconeogenesis is upregulated. Lactate, more amino acids, and glycerol, because now fatty acids are released by the adipose tissue. Fatty acids are coming to the liver for beta oxidation and supplying energy for gluconeogenesis. Ketone body production is upregulated from fatty acids because these ketone bodies, lipid-based energy, started to be used by muscle tissue and also by the central nervous system. Proteolysis is going on in the muscle to produce amino acids, to supply amino acids for gluconeogenesis, and because amino acids are coming to the liver, urea cycle will be upregulated there. So these are the pathways that I talked about going on, and I would like to also start to introduce that storage fat which is liberated and ketone bodies that are produced by the liver will be used for lipid-based energy. Liver, muscle, kidney will take up fatty acids. Liver produces ketone bodies and mainly the muscle which will be using that. Glucose is still utilized, majorly the central nervous system, which will always need glucose, and all the anaerobic cells will utilize glucose. So what if we fast further, intermediate fasting period? There is no glycogen anymore. We use it up completely. No fuel is coming from the gut still. So gluconeogenesis will be highly upregulated, as high as the enzyme level will be increased in the liver, in the hepatocytes. So the transcription of the enzymes will be upregulated too by those hormones. So liver will be using lactate, obviously, amino acids coming from the muscle tissue, glycerol coming from the adipose tissue when triglycerides are hydrolyzed. Lipolysis in the adipocytes, highly upregulated. Ketone body production in the liver, highly upregulated because these fuel molecules are heavily utilized by every other cell of the tissue. Proteolysis by the muscle cells is also upregulated, of course. So this is intermediate fasting. Again, these are the hormone-sensitive cells. And what you see is that still nothing is coming from the gut, but the gut needs to be fed. If the enterocytes are not fed, then they will shrivel and die away. So actually this is also an amino acid glutamine, which comes from the skeletal muscle, which will be used by the gut, by the enterocytes to get energy. So alanine is going to the liver, lactate is going to the liver, everything will help to produce glucose, including glycerol from triglycerides. Fat is going to the liver to produce, through beta oxidation energy, but also ketone bodies. And you see that ketone bodies start to be utilized by the central nervous system, and ketone bodies are also highly utilized by the muscle. So storage fat is a major source, liver, muscle, kidney, heart. Ketone bodies are utilized by muscle, heart, kidney, and started to be utilized by the central nervous system. Glucose is still utilized by the central nervous system, but tiny little bit reduced level because ketone bodies can supply energy, but there is no choice for the anaerobic cells. Glucose is needed for them to produce energy. Now, last stage is starvation. Advanced long-term fasting. Gluconeogenesis must go, but you see there is no double arrow here. It is a single arrow. Why? Because the amino acids started to be minor source. Proteolysis is still going on, but a very reduced level. Why? Because we want to spare our protein. If all the proteins would be utilized, we would be dead. So proteins need to be conserved, still utilized, but they will become minor. What is becoming major? Lactate and glycerol, because lipolysis is still going on until the stores are there. In long-term starvation, fat stores, adipose stores, are also getting low. Ketone body is produced, but it is getting low. This is the stage when thyroid hormones are sending the signal to the body that there is not enough energy. Slow down. So, storage fat, muscle, heart, and kidney. Please observe even ketone bodies are spared for the brain, and glucose is supplying at a low level to the central nervous system and all other anaerobic cells. Now, we are lucky we start to eat again. So fuel molecules are coming in again through the portal vein to the liver, amino acids and glucose, and fat through the lymphatic in the form of chylomicron is again distributed. However, something is fishy in the liver. What is fishy here? Let's compare and contrast the well-fed state and the refed state. So same things are coming in, insulin is released, same things are coming in. We are feeding every cell, happy, happy, happy. Now, let us concentrate on the liver. So amino acids are coming in, proteins are synthesized, and amino acids are distributed to the other cells. Amino acids come in, protein and synthesized, distributed. However, do you see these funny things? Amino acids are used for glycogen synthesis. What is going on here? Why not glucose? Glucose should be used for glycogen synthesis and for fat synthesis. There is no fat synthesis here. Why? Because the glucose is still coming in and going out. Why? Because glycolytic enzymes are not there. After long-term fasting, there is still the gluconeogenic enzymes that will use amino acids to produce glucose, which will be turned to glycogen. Now, it's not forever, of course. It takes a couple of hours to replenish the liver with glycolytic enzymes and eliminate gluconeogenic enzymes, and that everything is going back to normal. All right, so we went through a lot today, so let me use the couple of slides now to summarize what you learned. So what we did is focusing on liver. We had the well-fed stage when the liver is storing away glucose, running glycolysis for energy, and also feeding into synthesis of cholesterol and fatty acids. Fatty acids, triglycerides, are stored away in the adipose tissue. Well-fed stage, storing everything away, insulin. Starving state is independent of which stage we are talking about. Insulin is not signaling anymore, glucagon epinephrine is. So the liver switches to glycogenolysis to produce glucose, gluconeogenic to produce glucose, later on ketogenic to produce ketone bodies, and proteolytic to use those amino acids for gluconeogenesis. Energy reserves between meals is mainly glycogen, and in fasting mostly fat, and some proteins. Please remember, ketone bodies are produced and released by the liver. So how did we ensure caloric homeostasis, which means constant availability of the fuels for every cell in the blood? Blood glucose is one of the sources which has a very tight concentration limits. It cannot be too high or too low. The fatty acids, which have a variable source depending on whether you have eaten or you are between meals or you are in the fasting starvation mode when a lot of fatty acids will be released by the adipose. And ketone bodies also are a very variable source. Nothing is there until you have enough glucose, but when the glucose level is dropping, then ketone bodies start to be produced. Now, this is something that you can use when you review for this material. You remember that we went through, and now it is focusing on glucose homeostasis. We went through well-fed, between meals, starvation, short-term, longer term, and very long-term starvation. So it was between meals and short-term starvation, long-term starvation. This table lists you what is used for energy and what is supplying energy. And this table is actually really good for reviewing because what it says, these are the 5 stages of from well-feds to long-term starvation. It is focusing on where does glucose come from. This is focusing on this portion is focusing on what is using glucose, and then this column here shows you what the brain, the central nervous system, will use. One thing that I wanted to draw your attention to, when you learned about gluconeogenesis, you remember I said that it is mainly liver, hepatic function, but when we starve, kidney can help. So you see it here that it is hepatic gluconeogenesis. And now in longer term starvation, the renal gluconeogenesis producing smaller amount of glucose is becoming very important. This is again a figure that is helping you to understand what is going on in this feed-starve cycle and glucose and energy caloric homeostasis. And finally, this is the summary of the lecture. At first, we went through of the different typical cells, what happening there, what they can use, what they can take up for energy, and what they can potentially release. We focused on the central nervous system, red blood cells, skeletal and heart muscle, adipose tissue, and liver. Then we switched to glucose and caloric homeostasis. We defined which hormones will act on those 3 cells that are hormone sensitive. We went through the glucoregulatory system through these hormones. We talked a little bit about hypoglycemia, and we demonstrated through the feed-starve cycle how these organs, tissues, cells can work together to support all the cells of the body with calories and with glucose. We went through well-fed stage, short, medium, and long-term fasting. We took into consideration energy sources, organ source for different energy-carrying molecules. And we ended up with focusing on liver, and we ended up with putting everything into context of calories, caloric homeostasis, and glucose. Now, if you have time and you studied this material, I would like you to click on this link. I found a video on YouTube which I really like. Why? For 2 reasons. One, we talked about glucose, so it will show you that glucose is the main source of our energy. but it also will show you what happens if too much glucose is taken up by us. And it also relates to a later lecture, which is talking about diabetes and the consequences of high circulating blood glucose. So enjoy.